Yes, just saying Linjian is here joining us from Illinois, and where he works kind of interdisciplinary way between computer science, quantum computing, and tensor networks. So he's going to be telling us about work combining these.
Okay, yeah. Thanks, Miles. So hi, everyone. My name is Linjian. So I'm a PhD student at UIUC. So today I'm going to talk about low-rank tensor network approximation algorithms for quantum simulation. Let's see. So tensor is a multidimensional array of data, and in this presentation, I'll widely use tensor diagrams to represent different algorithms and tensor networks. So tensor network represents a high-dimensional tensor with a set of small tensors and a specific contraction pattern. So the first, here I show some widely used ones. And the first one is called a Kronecker product, and you can think of this one as a rank 1 tensor. So basically, there's no dimension that connecting any vectors in this product. And the second one is called canonical polyadic or CP decomposition, and this kind of format is widely used in the tensor decompositions in data science. And a CP decomposition is actually just a sum of multiple Kronecker products. So there's one dimension that connects all these matrices. And the next are the Tucker and matrix product state, and also hierarchical Tucker. These are both tree tensor networks. And we also have a non-tree or general graph tensor networks, including tensor rings or PEPs, which is a 2D network. So quantum circuit, we can think of this one as a specialized tensor network. And it's a unitary transformation of a quantum state, basically perform a unitary transformation U times the input state psi. And in general, quantum simulation directly is pretty hard. This is because when we increase the n, we have exponential cost in terms of both the memory and the computational cost to represent both the absolute psi and also compute the unitary transformation. However, in general, a lot of famous or well-known quantum algorithms have specific structures. In particular, the input and output states tend to have low rank structure. So for example, the input state, usually, for example, they can be rank 1, like the order product or tensor product of 0 state, or they are the superposition of order states, which is the tensor product of plus state. And output state, they also usually have a low rank structure. For example, many algorithm has an amplitude amplification feature, means that there's only a few elements with large amplitudes. And each gate is a 1 qubit or qubit gate is also actually can be represented low rank. So today I'm going to talk about 2 parts. The first part, I'm going to talk about how we can use CP decomposition to analyze the rank of several famous quantum algorithms. And actually with specific inputs, these famous quantum algorithms have low rank properties. And the second part will mostly be on the numerical algorithms. I'll talk about how can we use randomized techniques to accelerate low-rank tensor network approximation. And these techniques can be used in quantum circuit simulation. Basically, if we want to do the truncation, we can use these techniques to accelerate our algorithm. Okay, so this is the outline of the talk. At first, I'll talk about use CP decomposition for quantum circuit simulation. Then I'll transfer to the algorithm, numerical algorithm, and the review of the standard algorithms for the low rank approximation. This includes hierarchical SVD and alternating least squares. And then I'll talk about our new results that applies the randomized sketching techniques to accelerate this algorithm for CP decomposition and the MPS truncation and so on. Okay, so let's first take a look at CP decomposition. CP decomposes a tensor into a sum of rank 1 tensors. So here, this is the expression for the case where the input is a 4-order tensor. We can represent that one use a tensor diagram that's just a summation of multiple rank 1 Kronecker products, or we can just use one dimension to link all these vectors so that it has 4 factor matrices A, B, C, and D. You can think of CP as a specialized MPS where it has more like symmetry structure. Also, it has some property that applying, for example, swap gates, if we want to swap some indices, for example, the one adjacent to A and C, it will be very straightforward. While for MPS, maybe we need to do like truncation and then SVD. So this is kind of simplified and then simplify some of the operations. So what we can do is that we represent the input quantum state for the quantum algorithm as a CP decomposition. And then every time we apply the quantum gate, maybe the rank will increase. Then we can decrease the rank by using some truncations. So applying 1 qubit won't affect the CP rank of the state, and applying 2 qubit will at most double the CP rank. And this is because we can easily like rewrite each 2 qubit gate as a sum of 2 Kronecker products. For example, here for the controlled U gate, we can rewrite that one as E1 Kronecker product with identity plus E2 with this U. And this E1 and E2 just the projectors onto the 0 state and also the 1 state. So then we can, for example, if the input state is rank 1, then applying this gate to that will at most have like rank 2. But for the special cases where the A can be 0 state, for example, or 1 state, then one of the term will disappear. Then actually applying 2 qubit gate will not increase the CP rank. So this is a very simple rule, but just using this rule, we can analyze several quantum algorithms and show that they actually internally have low rank with specific input states. Okay, so let's first take a brief look at QFT. So Chris just gave a very good talk on using MPS to simulate QFT. And then here I'm going to do a simple analysis. So let's look at using CP decomposition and what kind of results can we get using to simulate the QFT. Let's first look at the case where the input state is a rank 1 state, and it's also a standard basis. So basically the input to each qubit is just a 0 state or 1 state. Then we can easily see that every time we apply a controlled qubit, the controlling the input factor to each controlling qubit will always be either 0 or 1 state, so that the control qubit controlling gate will not increase the rank. So so this actually shows that if the input is a standard basis, all the states, intermediate state and alpha state, will be just rank 1. If we get a superposition of this standard basis, the rank will also not change. Unfortunately, for CP decomposition, when the input is a random rank 1 state, it's unclear whether the circuit will generate low rank, like low rank states, intermediate state, and alpha states when we do the simulation. So this one is also verified experimentally. We see that the rank will grow pretty fast. And also I want to mention that there are existing work, and Chris also mentioned that using MPS, we can get like a pretty low rank along low MPS rank when we do the simulation. But MPS, when the MPS rank is low, it's also possible that CP rank is pretty high. So it's kind of just choosing different answers can get very different results. So the second algorithm we can analyze is a phase estimation. So for phase estimation, we are given an oracle unitary U, and we also have an input that is one eigenvector of this unitary psi, and we want to analyze we want to get the eigenvector or the phase of this eigenvector. So the phase estimation circuit has 2 parts. In the first part, we have several controlled oracle gates, basically to encode the phase information, and then we will like output the information by doing a QFT inverse gate. We first look at the first part where before the part of the circuit before this QFT inverse. We can easily see that all the intermediate states in this first part will have rank 1 on the first register. So this is because we don't know what's the rank in the eigenvector, and it can be pretty general. So the first register, all the rank will be 1. And we can actually explicitly write the input to this QFT inverse gate into this rank 1 expression. And as to the QFT inverse part, we can actually bound the error when we have a bounded fidelity. So basically, we can analyze that all the states inside this QFT inverse will have rank upper bounded by 1 over epsilon when the fidelity is at least 1 minus epsilon. So this means that if the epsilon is some constant like 0.01, then we can still get a constant CP rank when we want to do the simulation, and the results are still pretty accurate. Although here we assume that psi is exactly the one eigenvector of U. When this one is not, it depends on how we can write psi as a superposition of multiple eigenvectors. Then that will also decides what kind of low rankness we can get for these states. We can also analyze the Grover's algorithm using CP decomposition. So the goal of Grover's algorithm is to find a particular item X star from a set that contains this item. And what it does is that it encodes all these items into the states. So for example, we can let X star to be all ones state and also other items to be encoded here. And then applying the Grover's operator for the square root n times so that we can get a quadratic speed up. So Grover's operator contains two parts. The first part is the oracle unitary. And what this unitary does is that it kind of encodes the information for the marked item. And then there's a diffusion operator UD. Basically, it diffuses with the center being the H state, which is a superposition of all the states. So what the Grover operator does is that every time we apply this operator, so basically, when the input is just a H state, which is superposition of all states, every time we apply this UG, all the intermediate states will be in the subspace spanned by this X star, which is the marked item state, and also this H state. Basically, every time we apply this UG, the magnitude on top of X star will increase. And finally, we can output that item with high probability. But this directly means that the rank will be bounded by 2. So it's a very low rank in terms of the CP decomposition. And also, this rank is also low, like inside this diffusion operator, so that everywhere in the Grover's algorithm, the rank will be very low. For the general case where we have multiple items that we can search in the Grover's algorithm, the rank will be bounded by the number of marked items plus 1. So if the marked subset is still small compared to the set, for example, if the number of items in A is a constant, then it's still a very low rank algorithm. Okay, so briefly summary, several famous quantum algorithms with specific inputs can be efficiently simulated by CP decomposition. And this is also consistent with some existing results that showing that, for example, QFT with specific inputs can be dequantized. I think this result is using like MPS input. And also Grover's algorithm is not relying on the entanglement too much to provide the speed ups. Yeah. Okay. Yeah, that's a question.
Just assume that the input state to Grover's algorithm is also weakly entangled.
Yeah, I think standard. So the standard input to the Grover's algorithm is just a superposition of all the states, which is rank 1. Yeah. Yeah. Oh, okay, Miles.
For the phase estimation, that's really interesting. Did you have any thoughts about just if the second register, the input state is not quite an eigenvector, like what if it's just close to an eigenvector, how that many things might go?
Oh, yeah. Good question. I think it depends on how we can expand that one as a sum of multiple eigenvectors. So we haven't like done experiments on that. Yeah.
So if it's something like if it's a sum with a small number of eigenvectors,
Yeah.
that might be
Yeah, exactly. Yeah. Okay, so I think I'll go to the second part of my presentation. So for many quantum algorithms, it's actually a little bit hard to analyze the rank theoretically. For example, if we want to analyze the rank of some random quantum circuits, what we actually want to do is to simulate these algorithms using low rank approximations and using experiments. So a low rank approximation, here I define this one as a general technique that approximates a given input tensor network with a low rank tensor network. And the graphs of these two can be different, but they can also be the same. For example, if we can, we have already talked about the algorithm to truncate the MPS. Basically, for that problem, it's just a truncation problem that the input and output graph are the same. But in general, this is like a pretty general system, like a problem that we can look at. I'll talk about how we can use hierarchical SVD and alternating least squares to optimize this low rank approximation. First, let's take a look at hierarchical SVD. So this kind of scheme performs a sequence of SVD to update the low rank network. And you may see different names for different configurations. For example, for the MPS or tensor train is sometimes called TT-SVD. And for the Tucker decomposition, it's called high order SVD. And so it also has different names. So this kind of algorithm will be pretty accurate when the output network has a tree structure. Actually, the accuracy comes from that it also has theoretical bounds for the error. So here I show one example that how do we do hierarchical SVD for the balanced binary tree tensor network. In the first step, we look at this left leaf, and we regard the whole network as a large tensor. What we do is that we just perform a truncated SVD that separates the left two output dimensions and the right dimensions, and then do the truncation. And then the singular vector is used to update this leaf, and all the singular value information are pushed to the environments. So basically, all the other vertices represent this U transpose times T. And then we go to the next leaf and then update this leaf, and then push the singular value to the the remaining graph. And then we do this for multiple times until finally all the singular value information are in this root node. So this is just a high level idea of how this algorithm is doing. But practically, one can use multiple algorithms, for example, orthogonalization, to do this in an efficient way. Basically, we don't need to form this T explicitly. That is too costly. But internally, like the orthogonal then truncate algorithm is just doing this hierarchical SVD. So for the case where the output is still a tree tensor network and the input is not, we can also embed the input into some tree and then do the truncation. So this kind of hierarchical SVD is actually pretty general. One reason is this is pretty accurate and is standard for tree tensor network is that we have a theorem that can bound the accuracy. Basically, let T denote the input tensor network and T opt denote the optimal low rank tensor network we can get in terms of the error. And then we have this T hat be the output of this algorithm. Then the error we can get using this hierarchical SVD will be bounded by the square root of the tensor order times this optimal error. So when the optimal error is small, this algorithm also outputs something that's also pretty accurate. But for general graphs, we don't have this bound. So this algorithm may not just be suitable for general graphs. That's another tree. Here I show an example that how this one is done on top of the MPS. For MPS, one can choose, for example, the root to be on the boundary or on the center, and we can truncate from the left to the right. So here, let's say that the dimension size of the original input MPS is big R, and we want to truncate that one to small r, and the dimension size is denoted as S. Then the most efficient and standard algorithm is to do the orthogonalization and then do the truncation. So the orthogonalize means that we want to do a sequence of QR decomposition from the right to the left, so that all the singular values are in this leftmost matrix, and others are all orthogonal matrices. And then to do the truncation, we just truncate this or do the SVD for the leftmost matrix, and then use that one to reduce this bound dimension and update the second tensor. So this orthogonalization is the most time-consuming one, since it has a cost of S times R to the cube. And this is because doing the QR is pretty expensive. And there's some other algorithms, for example, density matrix algorithm, but for this problem, it has the same cost. Next, I'll show that we can use some randomization techniques to reduce the cost to n times SR squared times n times small r. So we can see that when the small r is much smaller than big R, And especially the case where big R is greater than n times small r, using randomization can get a more efficient algorithm than the standard one. And I'll have some detailed explanation later. Yeah, okay.
I just have a question about the theorem about the optimal one. So I sort of see like term by term how when you're doing one, you do the orthogonalization and then you truncate, like that's optimal. But when you go down the line, it sort of has a left-right bias. You know what I mean?
Yeah, you mean
go further and you do all of them. So is that where you're picking up the square root of n?
No, so we assume that every time we do a SVD, we do that accurately. So this is because I can briefly talk about the error bound. So the error bound actually is proven by saying that every time we do a truncation, the error will be bounded by the optimal error. And then since we are doing n of them, we are bounded by square root n of that. Yeah. Does that make sense? Yeah. Okay. Sounds good. So next I'll briefly talk about another widely used algorithm called alternating least squares. So ALS is also called ALS. ALS iteratively solve a sequence of least squares problem to do the update. So let's use this example to illustrate. Let's say, again, we want to optimize the input T, which is a balanced binary tree, into this low rank one. And we have some initialization on this low rank balanced binary tree. So what we do is that we fix some of the factor matrices, so those in the part L, and put two of them as the variables. So this is the root and the left child of this root, and then optimize, just solve for this least squares problem. Then we use these results to we use these results to update these two tensors, and then we change the variable to some other two tensors, for example, the root and the right one, and then do the update. Basically, we reframe the nonlinear problem into a sequence of least squares problem and solve again and again until we get pretty good accuracy. So the advantage of ALS is that every time we solve a sub problem, the accuracy will guarantee to increase. So this is a monotonic optimization algorithm. For tree problems, what one usually do is that one use hierarchical SVD to initialize the factor matrices, and then use ALS to again improve the accuracy a bit. For non-tree graphs, what one usually do is just to use ALS to solve until convergence. Go back to the CP decomposition. CP decomposition has a very special structure that there's one dimension that connects all the factor matrices, so that this is not actually a tree structure, it's a pretty general graph that is a bit hard to optimize. So ALS is the most widely optimization algorithm that you use to optimize this problem. So in each small problem, one fix, for example, B, C, and D, then only optimize A. And this is again a least squares problem where the left-hand side is just a tensor network. You can think of this one as a general tensor network. Again, next I'll show that using randomized sketching, we can also to accelerate this ALS. Okay, so let me see. Next, I'll talk about how we can apply sketching techniques to low-rank tensor network approximation. First, I'll briefly talk about the background of sketching technique. So this technique has been widely used in numerical linear algebra, basically to accelerate some matrix problems. But there's open field of how can we also apply this one to tensor networks. Sketching randomly projects a high-dimensional data. Let's say we have a data A to low-dimensional spaces. So what it does is very simple. It just multiply a random matrix S to the left of A. We can also multiply this one to the right, by the way. For this case where S is left multiply A, we denote the number of rows of S as the sketch size. and M is usually way less than the number of rows of S, which is small s. And this S is also called embedding. So we embed this A into some low dimensional spaces. And then for a lot of numerical linear algebra problems, we just run these computationally expensive algorithms on S times A. For example, we can do SVD. So this is actually just a randomized SVD algorithm. We can do least squares. So it's actually a sketched least squares problem. We hope that this sketching, projects A into some low dimensional spaces. So it's more computationally efficient, but we also hope that the output of the sketch solution can be close to the original solution so that it will be accurate. One important property of the embedding S is called epsilon delta accurate. Basically, we hope that for any vector or any data, this S times X, the norm will be very close to the norm of the original vector. And this can happen with, we hope that this will happen with high probability. And this is called the epsilon delta accurate. And this is also discussed in the pretty famous Johnson-Lindenstrauss lemma. It seems that this property is only talking about how we can preserve the norm for sketching multiple data. But this property is actually implies accurate SVD and least squares problem when we apply the embedding. Here I briefly talk about how we can use this sketching technique in the randomized SVD algorithm. Randomized SVD, the goal is that we are given a matrix A, let's say with size m by n. We want to find a rank R approximation with R smaller than m and n. It has multiple steps. The first step, we just multiply A with a random matrix. For example, we can multiply this one on the right. Then to reduce the number of columns of this A, we then do a QR decomposition of this A times sigma, and then get the Q, which is the left singular vectors of this A. And this Q is called the randomized range of this A, and this procedure is called the randomized range finder. Once we find the randomized range, which is a range of A which is approximately the range of A, we then left multiply this Q with this A to reduce the dimension of these rows. And then we just do a SVD on the low rank matrix Q times B. Since Q is an orthogonal matrix, we can do that just by doing SVD on B. And then Q times the left singular vectors of B will be the left singular vectors of this A. The second application of sketching is the linear least squares. We are given a matrix A and the right-hand side vector B, and we want to solve for this problem. So for sketching, we simply just multiply this random embedding to both the left-hand side and also the right-hand side, and then solve for this sketch problem. We can design the embedding so that this problem is more efficient than the original problem. Also, when the S is accurate, for example, when it's epsilon over n and delta accurate, then this implies that the least squares problem is also accurate up to a factor of 1 plus epsilon. So this kind of connects the accuracy of embedding to the accuracy of other problems. Here embeddings, the sketching algorithms have been applied for matrices. But for the cases where we have tensor networks, for example, Ian just mentioned like a tensor network regression, where, for example, A is a tensor network, then if we want to apply sketching techniques, choosing S as just some random Gaussian embedding, Gaussian matrices will be very inefficient. So then that gives us a problem of how can we design this embedding so that this can also be efficient for the tensor networks. Okay, so this brings us a problem that we solved recently. So we look at a problem that we are given a tensor network input data X. This can be like an arbitrary or general tensor network. We want to find some tensor network embedding as such that the embedding is both accurate and is efficient. So the efficiency has multiple parts. We want that the sketch size of this S to be very low so that later downstream tasks can be performed in an efficient way. And also the cost to computing this, to do the sketching, basically multiplying this S by X to be minimized. These two figures are kind of some of the visualization. We have some data, and this can be some general tensor network. We want to apply something on it, and these gray vertices are the random embeddings. So the question is what kind of structure can we choose in the embedding so that this problem can be efficiently solved? Existing reference previous work look at multiple embedding structures. For example, in the 2020 paper, they just explicitly show that the canonical product embedding will be inefficient in computational cost. This is because if we apply a canonical product embedding for this to be accurate, the output sketch size will be too large for later tasks to be efficient. And there's also work that discuss tree embeddings. This includes the MPS embedding, where we just make this embedding an MPS structure. This has been shown to be pretty efficient for specific data, including the MPS, but the efficiency is still unclear for general tensor network data. Yeah. Okay.
Are you thinking here of the data already having a certain kind of like low rank structure for these ideas to be usable?
Yeah. So we don't assume it's low rank, but we assume that we know that it has a low tensor network structure defined on some graph. Yeah.
For efficient application of the embedding in the matrix space, are you assuming that it's in the sparsity or?
Yeah, good question. Yeah, so for the matrix case, one big topic is how do we sketch it efficiently in the sparse case. For tensor networks, in this work, we haven't talked about sparsity, but there's still also work that basically want to design embedding so that it's efficient for tensor networks, also efficient for sparse matrices.
No, I'm saying the sketching itself.
Oh, itself? You mean each matrix in the tensor network is sparse or
in the
overall?
Sketching. The network is dense, but for the matrix, but the sketching matrix.
Oh, okay.
Sparse.
Yeah. So we can choose it to be some dense embedding or sparse ones. So here we only talk about Gaussian embedding, where each element is just a Gaussian random variable. So this is a dense embedding. But there's work that use, for example, it's called consketch, which only have, for n by n matrix, only have n non-zeros. This is a sparse embedding, but yeah. Sure.
There's a question in the chat. You could repeat it and then respond to the question. What does it mean to say the data is tensor network data?
Okay, so the question is, what does it mean to say that the data is a tensor network data? So you can think of the data to be a vector or a matrix, but it internally has a tensor network structure. For example, it can be a canonical product or MPS. So yeah, that's just my answer. Yeah. Okay, so I'll continue. So in our analysis, we look at what kind of embeddings are efficient for general tensor network inputs. Although we still have some assumptions in our analysis, we're assuming that every matrix using the embedding and data is dense, so that the matrix multiplication are done using the classical algorithm with a cost of n to the cube. And also, we consider embeddings defined on graphs with no hyper edges. Basically, some like a CP decomposition embedding is not considered here. And also, each dimension to be sketched has a size lower bounded by the sketch size. Basically, this means that we assume each edge that connects the embedding to the data has pretty large size. And this is just for the simplicity of the analysis. When the size is not large, for example, in the quantum circuit simulation, this size may be 2. We can also use some embedding, tensor network embedding, to efficiently sketch. Okay, so first we present a sufficient condition for the embedding to be accurate. So the sufficient condition is that we can rewrite every embedding, tensor network embedding, as a chain of matrix multiplication, where each Si is some canonical product of identities with some random matrix, and Pi is just some permutation matrix. And if each AI that is used has row size lower bounded by a term that's proportional to the number of tensors, then this embedding will be accurate. So briefly speaking, what we are actually doing is that we are given an embedding and we find a linear ordering of these vertices so that we can rewrite this embedding as something on the right. And this linear ordering gives us a way to matricize each tensor. And for each this matricized tensor, if we can just have a lower bound on the number of rows of these matrices, then we can get a sufficient condition. So using this condition, we actually bound the sketch size for different embeddings, including MPS. So we are able to show that if we have an MPS embedding shown here, where each size of the dimension is just m and the sketch size, when the m is on the order of n times some factor, which is linear in n, then the embedding will be accurate. While the previous results show that this has an exponential dependence on the number of tensors and is not as efficient as ours when the n is pretty large. So these results actually just also show that MPS embedding is pretty good for several tasks, since the linear dependency is kind of almost optimal as what we can get for the sketch size. Yeah. Now, yeah, so each tensor in the embedding is a Gaussian tensor. Yeah. Okay, so on top of this sufficient condition, we provide a sketching algorithm with efficient computational cost and also the sketch size. So the sketching algorithm is using an embedding looking like something like this, shown on the left. It has two parts: the canonical product embedding part, where we apply each matrix on the dimension that we want to sketch. This is used to reduce the dimension size of each edge. And then we have a binary tree embedding. So in this binary tree, each vertex is a small tensor network that contains two tensors. And this part is used to reduce the dimension size every time we merge two indices. So this is has a high-level tree structure, but also it's actually just a general graph rather than a tree embedding. So the algorithm is that we are given a specific data contraction path, and before the output data dimensions are merged, we apply this canonical product embedding, and every time we merge two tensors that has sketch size, has sketch dimensions, we just apply one vertex in the binary tree embedding. So here I want to show this, illustrate this using an example of sketching a canonical product data. Let's say we have a data that's having this structure, which is a order 4 canonical product, and we want the first one to contract with the second one, then with the third one, then to the right. So this is the green dots shows the contraction path for this tensor network. So the sketching contraction path will be as follows. We first multiply each vertex, each input data matrix or vector by this random matrix in the canonical product embedding. This is used to reduce the dimension size, each dimension size. And then every time we merge two data tensors, we just apply one vertex in the tree embedding, basically to reduce the dimension size, and then do this one multiple times until we only have one tensor. So this is almost the optimal algorithm, and is also faster than the existing work that use only tree embeddings. Sorry, we also have some analysis of the algorithm. So let's see the asymptotic sketching cost for our algorithm, and let's see the optimal sketching cost under the sufficient condition, which is the lower bound cost that we need to use. That m to be the sketch size, when the input data is can be defined on a general hypergraph, then our algorithm is optimal up to a factor of square root m. When the input is a general graph, the approximation factor is reduced to the m to the smaller polynomial number. When the input data is something like an MPS or Kronecker product, which has a property that each data tensor has a dimension to be sketched, this is the optimal algorithm. And then our algorithm is actually achieve the cost lower bound. Let me see. Okay, so I guess I'll skip the experimental results. Basically, this show that our embedding, which is shown in the blue one, has better cost than the existing ones. Although in the some of the regimes, they also perform similarly. I want to show how to apply this one to the CP decomposition. The algorithm is pretty simple. It's just instead of solving an exact least squares problem, we apply a sketching matrix on both the left hand side and also the right hand side. And this sketching matrix is used based on our sketching algorithm, basically a Kronecker product done with a tree-like structure. Here I skip all the detailed analysis, but when performing this low rank CP decomposition, we achieve better cost than the existing ones. Although one disadvantage of our current algorithm is that this algorithm is not very efficient for sketching the sparse matrix. So especially here, when we want to apply this embedding to this very large tensor that's potentially sparse, our algorithm now costs larger cost, and here I call it preparation cost. And this cost can be reduced when we use like more sparse embeddings. So, and we leave the analysis as the future work. Yeah.
So your bounds explicitly assume Gaussian.
We assume Gaussian embedding. Yeah. Miles.
In this figure, is the gray box to be this whole graph that you showed?
Yeah. Okay, so next I'll briefly talk about how we can use this algorithm to accelerate SVD. MPS truncation. So we can reduce the cost from n times s times r to the cube to n as r squared times n to the small r. So this has a better dependency on the big R. And when the small r is way less than the big R, this will be more efficient. So the algorithm is that it has two steps. The first, we apply a sequence of randomized rangefinder to reduce the bound dimension to small m, which is big N times R. I'll talk about the details of how do we perform this randomized rangefinder using our embedding. So basically, this has less cost than doing the orthogonalization, but it reduces bound dimension from a black one, which is big R, to this kind of a smaller one, which is proportional to big N times small r. And then we just do a standard truncation algorithm that truncates this bound dimension again to small r. But this algorithm doesn't have a dependency on the big R. So it's not the leading cause. The leading cause still doing the randomized rangefinder. This randomized rangefinder is done in just using a sequence of randomized SVD type of truncations. Basically, here I show some of these steps. When we want to truncate this first bound dimension, what we do is that we apply this tensor network embedding on the right 3 dimensions. This embedding can be chosen by our algorithm, then the cost will be pretty efficient. Then this will give us a pretty small matrix, and then we just do a QR on top of this small matrix. This output a Q, which is here I call it U1, which is the leftmost singular vector matrix, and then we apply U transpose to the MPS to reduce the tensor number to this smaller MPS. Then we again apply this tensor network embedding on the 2 right dimensions of this small MPS and get U2, and then do this swap again. So after it's finished, it's just we have a sequence of orthogonal matrices. So this green ones, and then we also have one tensor that contains all the singular value information. So this step if we analyze in detail that using our embedding, then we can get a better cost than doing the orthogonalization. And this is how we accelerate this problem by introducing this embedding. Yeah. Okay. So here some discussions. Here we assume that each physical dimension size is greater than the output MPS rank. For some problem, it's not very practical, but when the like physical dimension size is smaller than this R, we can still using our embedding, but we just remove the Kronecker product part, but can still yield the same cost. We also want to mention that this cost actually attains the lower bound cost under the sufficient condition and under the Gaussian embedding case. There's previous work that use this MPS type embedding on the MPS truncation, and our algorithm and their algorithm also have the same cost, and this is because for this specific case, MPS embedding is also pretty efficient. Okay, so there's some following work on this input for this tensor network sketching, like generalize the analysis to other embeddings and also to consider the other data tensors. For example, those without the assumption that each dimension to be sketched has large size. And these are our following work. So I want to mention that this sketching technique is not only useful in low rank approximation or least squares, but we can also use that in some other applications like approximate a contraction. Basically, if we have a tensor network A and B, we can approximate that one by inserting two embeddings in the middle. And also, tensor network regression that Ian has mentioned, we can also use sketching to maybe accelerate that one in terms of the classical case. And also low rank approximation, if we don't want to use a randomized SVD, we can also use a method called generalized Nystrom algorithm. Basically, we insert some of the embeddings in the middle. So we apply sketching in both the left and right hand side of this data A, and then apply the embedding. So this already gives us a low rank structure of this matrix. But Nystrom algorithm is more efficient than randomized SVD, but it doesn't give us a SVD format. So it doesn't give us the singular vectors. For some cases, this can also be used. We can also apply our tensor network sketching technique to this problem. Yeah.
You explain when this approximate contraction would be, in which situation it would be useful?
Yeah, so for example, MPO times MPS. If you have two MPS, you want to, for example, multiply them together, maybe insert the embedding in the middle can reduce the cost, but it also reduces some of the error. But just some thoughts, yeah. Okay, so I think I have 10 minutes. So I'm to briefly talk about some of the work that I'm currently working on. So this is a system for the efficient contraction of tensor networks. So in general, arbitrary tensor network is very hard to contract, and one way we can do is that to contract them in an approximate way. So what we do is that we are looking at the format algorithm that we are given this tensor network and also given a partition of this tensor network into multiple parts, and also a contraction path on top of this partition. Every time we merge two partitions, we want to approximate the output tensor as a tree tensor network. And we want to use several low rank approximation techniques so that this tree will be low rank and will be efficient for the later contractions. And this tree structure is also chosen so that we want to minimize the computational cost for the later contractions. And we are currently using multiple heuristics to trying to make the system efficient for several cases. And internally, we also want to use this system for the quantum circuit simulation. And this is something that we are currently working on. Yeah, and here I'll summarize my talk. I talk about two parts. The first one is using CP decomposition for the quantum circuit simulation, and also how we can apply this randomized sketching techniques to the low rank approximation. And thank you. And now to take questions. Yeah.
Moving back to this, slides ago we talked about sketching and contraction in media.
Yeah.
Is there any notion of what it means? Let's say A and B were not the same, not matching in size, but S transpose or something like that, sort of map them to the same size? Does that have a clear implication what you're doing? Like you take A and AB, where our A is 4 and B is 2, and your S transpose maps you from 4 to 2 and they contract. Is there a meaning to that operation?
You kind of reduce the contraction dimension of these two matrices. So
If you're approximating a contraction, it couldn't actually happen directly, but you're sort of mediating it by a random matrix. Meaningful.
yeah.
What does it mean?
Yeah, I mean, it can be, so you can think of, we like project A to some lower dimensions, also B to some lower dimensions. And if these embeddings are accurate, then these projected ones have very similar property as the original matrices. Then we multiplying them together can also be efficient or accurate. Does it make sense? Yeah. Actually, there is some bound saying that if the S times A is very similar to A in terms of the norm, then this mission multiplication can also have some like bounds in terms of the error. Yeah. Miles.
You know, or like, have you thought much about the bounds seem to be taking rather like general properties of the data or the tensor that you're trying to sketch? Like, do you know if there's some direction you can go where you can input additional structure, like about the tensor that you're trying to sketch, like you do properties of the elements or something about it ahead of time, or you could guess those properties? Would that help?
Are you talking about something like a symmetry property or sparse property?
For example, or like if maybe smoothness, like if you know some of the elements in the tensor are like related to each other. Okay.
For that, I'm not sure. Yeah. I think if the tensor element is sparse, there's some work that discuss this. But in terms of symmetry and the thing you talk about, I don't think, there's any work for that. Yeah.
Could you comment on the state of the implementation of this?
The algorithm?
Especially for the generic tensor network contraction, yes.
Oh, you mean this one or?
Yeah.
Okay.
At which
Which part?
stage is it at the moment? Yes.
Okay. Yeah.
Usable.
Okay, sounds good. So, we are currently testing. So the algorithm is almost implemented there. We just need to clean the repo a bit. And also we are testing on several cases, for example, 2D and 3D IC model, and then random tensor networks. I think, in several months, maybe 2 or 3 months, we will clean up the repo. And the repo, I'm already making a pull request to merge in this branch. And we will try to clean up the code, and then I think users can just use this one. Yeah.
Thanks.
Yeah.
Earlier on, you talked about the CP rank of these quantum algorithms.
Mhm.
Is there a clear meaning for the CP rank of like a multi-qubit system? How that connects to different properties of the state and the quantum state?
So I know that in quantum information, the CP rank is interpreted as the Schmidt. It's called the multipartite entanglement, the Schmidt measure of this multipartite entanglement. There's also work that try to bound the CP rank of a specific quantum state. And I think that can give us information for if we have a distributed quantum algorithm, what kind of information we need to transfer from one part to another, and so on.
So it's kind of weird, the generalization of the Schmidt for bipartite.
Yeah.
So this CP decomposition doesn't have this nice embedding property that you have in tree tensor networks, right?
Yeah.
Where the larger CP rank is not, a smaller CP rank is not included in necessarily in the larger CP rank approximation.
You mean in terms of can we design efficient CP embedding, something like
Let's
that?
say I have an MPS of some one dimension chi.
Uh-huh.
That's in the manifold of the MPS of one dimension chi plus epsilon.
Yeah, yeah, yeah,
But
yeah,
that's not the case for the CP decomposition.
yeah, exactly. Yeah.
So practically, you just scan from small CP rank to until you hit a sufficiently good approximation, or
Oh, you mean how do I choose the CP rank?
Yeah.
You just test, maybe start from something small. If it's not enough, then test something large.
Okay.
Yeah, I think just use heuristics. Yeah. Yeah.
So you can use embedding the speed of the MPS completion.
Mhm.
Does it also imply the speed of MPS times MPO? So just replace MPS with sort of like and the MPS and MPO, but they're not contracted together, but you just optimize.
Yeah. That makes sense. So I did some like a big analysis, I think. So yeah, we can accelerate that. But there's always one assumption when we want to use sketching for that. That is the final rank, low rank. We want that one to be much smaller than the original rank. So small r smaller than big R over n. So if the tensor order is too large and the rank you want to truncate is not doesn't have too much difference, I don't think sketching can be useful here. But if you want to truncate something like a 2000 to 20, maybe you can think of yeah.
Related to that, I was wondering about that factor. Because you might think if you did a very long MPS and things had local properties, that even the bounds might have an in it, that in that case sort of you could get away without needing to depend on the resources that you spend, like maybe you don't really need to scale up the size of the sketching and but is that like proven that you have to have this factor in the ranks, or is it like
yeah. So yeah, based on our experimental results, if we have n tensors, random tensors in the embedding, this kind of error scales linearly. So this n kind of is needed here. But we can choose to use smaller number of embeddings, not tensors in the embedding, but maybe use one tensor to sketch multiple small tensors in the MPS. So can use these techniques to maybe increase the accuracy. Yeah.
You mean like when you use patches or something?
Yeah.
Oh,
Yeah. But I haven't thought about that one. Yeah.